So, we had discussed about different ways by which a compiler can help in optimizing the code and optimizing generating an efficient code, which will save on the execution time. Today, we will see in this module, we will see some more measures which are taken. There are many measures, but we will not be able to discuss all of them. For example, there are measures on optimizing on the scratch pad memory. SPM means scratch pad memory, that means the number of the registers. Okay. There are optimization techniques by which we try to map in more number of variables onto the scratch pad, so that the memory references are reduced. But that we are not discussing in detail. We will be discussing two approaches which are specially useful. One is for multimedia type of applications, where embedded systems are having an increasing role. Another is our good old digital signal processing. All right. Now, let us first start with the digital signal processing scenario. If you recall, you will remember that in a typical digital signal processing architecture, we have got a address generation unit, right, which generates the address for accessing the arrays. So, typically in a DSP application, there are a lot of array handling involved. So, there are arrays, and I may like to access different parts of the array. Maybe I first access this one, then I access this one, and then I access this one, and then I access this one, like that, right. So, continually I need to compute the addresses of these indices. Okay. Now, for that, address generation unit is a part of the DSP, digital signal processor, because it allows us to do the address update along with the other updates. So, if we look at this slide once again, this was a typical DSP type of architecture, where there are address register files and there are the modified register files. Modified register files means a normal scratch pad, and here I generate the address, and from there I access the memory. Okay. Now, the key point is here, I have got say k address registers and m modified registers or scratch pads. Now, if I have immediate address register load, that means say I add a particular register value, increment it to 1, or I load it with a particular address, the cost of that is 1. Okay. If I modify it, the cost is 1. On the other hand, if we are given the auto increment and auto decrement facility, by which parallelly I can increment the register, I can auto increment by 1 and auto decrement by 1. If I can do this increment and decrement parallelly by hardware, then that is 0 cost, right. Therefore, let us first come once again here, that my accesses here are like this. I am accessing 1, then I am accessing 2. Now, this is not being achieved by auto increment, because I have got some address x, say this address is x, and I have to add x plus 1, 2, 3 in order to get this, and then, so this is y minus 2 to get z, right. So, I have to do, my traversal is like this, and which is not achievable using auto increment and auto decrement. Therefore, I need more number of computational cycles to generate the addresses. Right. Now, let us see how we can optimize it by finding out the proper layout. See, no one prevented me to come up with a layout where this one will be put here and this would be laid out here, all right, and this would be laid out next like that. So, that I could have done in an auto increment, I could have maximized the auto increment and auto decrement operations, maximize the number of accesses using auto increment, auto decrement method. So, that is our objective of finding an optimized memory layout. All right. So, let us look at this example. I am considering a basic block. What is meant by a basic block? A basic block, say this is something we did not discuss earlier, that say in a control and data flow graph you have got some points, some number of computations are coming up, and then there is a decision point, and based on this decision point you are doing some other computations, all right, and here you are doing some other computations. So, this is a basic block, this is another basic block, this is another basic block, where we are not taking any branching, all right. So, these are known as basic blocks. 1 basic block 2 like that, all right. So, now we are just considering one particular basic block, and say the variables in the basic block are A, B, C and D, okay, 4 variables, and suppose they are laid out in this way A, B, C, D, all right, sequentially. Now, the access sequence, the way the program is trying to access is that first it is trying to access B, then D, then A, then C, then D and then C. Consequently, let us see what will happen to this address register. First, the address register will be loaded with 1, so that it comes to B. Then the next access is D, therefore, this will be plus 2. Then next access is A, will be minus 3, right. Look at this mouse pointer. From D I have to do minus 3. Now, none of these are auto increment, auto decrement. After that, I am in now A, after A I access C, therefore, from there I have to do plus 2, again not auto increment, auto decrement. After accessing C, D. So, after accessing C I can do an auto increment, and after that again C, so I can do another auto decrement. So, these two are 0 cost, but I have got a cost of 4 already incurred. Now, with a little intelligent layout, I could have reduced on this. Let us see how. Say I come up with the layout B, D, C, A. Here the cost was 4. Why 4? Because I had to do the address computation 4 times. By the way, here I am not showing the instructions at all. I am just showing the addresses which I want to access. Okay. Only the addresses which I want to access. So, here again, so initially I have laid out B here, all right. So, I have to load it, no doubt I have to load it once. So, there is a cost, and after that B, D just by auto increment, 0 cost. Then from after D, A, I have laid out A here. So, I have to do plus 2. So, one more cost, right. Once again I have to do the computation. After I come to A, then C, auto decrement. From A to C I can come just by decrementing the address register. right. Next comes when I come to C, from there I have to go to D, and that is again by another auto decrement, no extra cost. After that D I have to come to C, auto increment, okay, no extra cost. So, the total number of load address register update cost is 2, okay. Thereby I can save on the time. Now, we have to see how we can arrive at this, how we can arrive at this. This we have done as a simple example, we will remain within simple example, but say suppose I have got an access sequence as I was showing here BDA CDC, all right. So, first I build an access graph, okay. The first thing that is built is an access graph, where each of the nodes are different accesses, and there is an edge between two nodes if they are adjacent accesses. So, B is adjacent to D, D is adjacent to A is adjacent to C is adjacent to D is adjacent to C, all right. So, that is how we form the graph. Now, we put weights on these edges. The weights on these edges are the same as the number of times this edge is traversed, the number of times this adjacent access is made. So, you can see here that after C I am accessing D. So, C to D is 1, and again D to C. So, this will be required, this consecutive access will be required twice. So, we form such a graph, all right. Now, from this graph we want to find out, now what do we want to find out? We want to maximize. What is our objective? Objective is to maximize, yes, maximize the auto increment, auto decrement operations. So, for that this adjacency graph will be helpful, and for that I will find out the maximal graph of this, maximal adjacent graph, and that will be this here, maximum weighted path here, maximum weighted path. You can think of a Hamiltonian path covering also. So, we get this, and this is exactly what we were doing here. The axis therefore becomes B. You could have started with A also, but the sequence would be same, B, D, C, A, all right. And for that, what will be my cost for this access pattern will be 2. In any case, I have to load B. So, that is how we get the memory layout. Now, what is it clear? We are finding out the maximum weighted path, so that all the nodes are covered. Okay. It will be applying the maximal spanning tree algorithm to cover all the nodes. Now, we can make more complex situations. So, there is now before this, let us present an algorithm for this, right. So, what do we do with this? So, suppose let us consider this first graph, this one. Let us consider this graph. So, we sort, I will put an example also with this, and we will build it up. We first sort the edges of the axis graph G, which is V E according to their weights, all right. That is first step. Then second is we construct a new graph G prime which will have V prime E prime with say G prime to be G and E prime to be null. Okay. We okay, to be null. So, we start with this graph, but the edge is not there, right. I am just defining it as B prime. So, what will I am having initially I am having the edge set being null, I am having A, B, C and D, and then so this is step 1, this is step 2, step 3 will be select an edge E belonging to E, all right, from the original graph. That is, if you look at here in this graph, that is G, which is having the highest weight. So, for us the highest weight is between C and D, right. So, if this now the decision is if this edge does not cause a cycle, then include it, all right. So, you include this with this edge too. Next. So, once we do that, otherwise we will discard it. Else discard. Okay. Now, we go on doing this. So, we go to this 3 till all the edges So, what is happening is I include it in E prime, right. So, I am adding it in E prime. So, go to 3 till all edges from G are selected. And as long as G prime has less than edges, okay, as long as it is not covered. So, what here as I move here, I have got a choice between all these 3. Now, if I include I suppose I include this A to C. So, all these are now next these are not covered. Now, next edge I select this one, that will form a cycle. So, I discard this, ultimately come to this, and this is my maximally weighted part. So, as I do this, this is only for the very simple case. For more complicated case, this algorithm, which is by Liao, who proposed this algorithm, all right, using which we can find out a nice allocation of this. Okay. Is the algorithm clear? So, that is a nice way of doing it. Now, this can be extended to more complex cases. Say for example, here is a case where it has been there are a little complicated access pattern, and so here not only the auto increment auto decrement minimization, we also try to utilize multiple auto increment auto decrement registers, because there can be multiple registers, and therefore, what has been done here is that you can see the access pattern is such. If you look at these are the control steps, you can see the first one is here, the next one is very close, there is a jump here. So, that will be a load here, and then again a load here, again a huge load here, and like this it is going on, right. Now, so here what has been tried is that how can we utilize minimum number of address registers, not one, but more than one, minimize on the number of address registers and minimize the number of loads. Thus, you can see that we can use two address registers A1 and A2. A1 can very well devote itself to these addresses, these accesses, and A2 can devote on these accesses. However, there are some cases where there are loads. Okay. Here there is no for auto increment. Yes, you can do that. Here also you can do. It is still auto increment, auto decrement, right, between clusters. So, you can see that here we are playing with two address registers A2 and A1, where we are playing the same game, and we are trying to come to a layout, so that we can minimize. Here we are having a loading cost of 2 in the earlier case, but if we had used two address registers, we could have minimized that. So, that is another way this can be achieved. Next, I will talk about another technique, very simple technique, very intuitive technique, that is very much applicable for multimedia applications. Typically, in multimedia applications, we have got large arrays which we handle, right. And the problem here is how to accommodate all these arrays into the memory, because in an embedded system we will have limited restricted memory. Okay. So, here you can see initially we have got arrays A, B, C, D, E, all right, 5 different arrays, and on this side is the addresses which are accessed on the y axis, on the x axis we are showing time. So, the typical array elements which are being accessed along the time is being shown by this graph. So, at this point of time, I can see that I am accessing this element as well as this element at the same time, and doing some addition whatever. So, we are doing here. So, this double ended arrows are showing the maximal range of array access. So, and over time you can see the array access of A, array access of B, array access of C, the addresses are all not the same. This is the addresses accessed. Okay. Now, typically or conventionally what we do? We do the array in an unfolded manner. I put array A here, array B here, array C here, array D here, array E here, and so much memory I need for all these arrays. But if you look at this diagram, one thing will strike you, that this one is accessing addresses which are overlapping with these, all right, these addresses over time. Now, if I overlay that arrays on the same memory, I can overlay them. I have got two arrays, I can put them in the same memory location when they are not being accessed at the same time. So, you can see that the addresses, if I put these two, fold them, that will not be accessed at the same time. So, I can put them in the same place, because this range will be accessed now, and the same range of another array will be accessed at a later point of time. So, I can swap this. Obviously, by that I have to have the swapping over it, but I am now considering the memory optimization. You see, all through these optimizations there are contesting parameters, right. So, if we have got this, and if I can fold this, I can fold it in this way, that address, these addresses are being accessed now, these addresses, this range of address are being accessed at disjoint times. So, I can simply put them in the same, decide to put them in the same locations, because they are being accessed at different points of time. And similarly, these two, their addresses are overlapped, but the addresses ranges are here, this is the range, but they are being accessed at disjoint points of time. This is known as inter-array folding. We can further look at this any particular array and analyze that and see which are the elements, sub arrays, which are being accessed simultaneously, and in the same way we can do intra-array folding also. Now, this has got some magical impact, the idea is so simple, but here is an application of DTSC optimization, where the modulo operations and the addition of and the division operations, division and modulo operations were replaced by unfolding and then by array folding. For example, here there was a mod operation in a loop. Okay. Here is, you can see that in a loop you are doing a mod operation, and mod operation is costly. So, that has been broken down, as since it was mod 4, this is an equivalent code, okay. And you can see that if the temp variable exceeds 4, you go over here. So, consequently what happened? So, you are implementing the mod in this way. Okay. So, there is a looping here. So, you can see the temp value is going on and then coming down here as soon as temp is 4, and then the next one is starting. So, in that way we could have played here. What we have done is we are playing with the indices, okay, playing with the indices, and by that you can see that is a typical result, that we have been able to using this technique of these two optimizations of layout and this, we could have reduced the time to a large extent, the number of cycles of a particular benchmark. Okay. So, that is just an example. The main point that I would like to emphasize are these two compiler optimization techniques. Okay. Okay. So, since I have, this is clear, right? Inter-array folding is clear to all of you. Now, if I look at this array separately, here I was looking at all the arrays together. Now, if I look at this array, here I will also find a temporal behavior, that some parts of the array, this part of the array and this part of the array are not being accessed at the same time. So, even within that array, that the particular memory location that memory locations that I was allocating for this array can be further reduced like this. This much has been reduced to a smaller size, because it can share the same memory locations depending on disjoint access over time. So, that is what we are doing further iteratively on intra-array. Okay. So, next we will move to, let us not have any break.